Okay, so welcome back, everybody, from spring break. I hope everybody had a good spring break. A quick reminder, don't forget that we have an exam coming up on Wednesday. And I hope everyone's had a chance to look at least a little bit of Math 216 over break to, keep yourself polished on that material. As we talked about before, we don't have time to do like review days before midterms. There's just too much material in the course. So today is new material, but it's new material that won't be fair game for the midterm, just for fairness reasons, right? Which seems weird right before the midterm, but there's just no other way around it. Okay. All right. So where we were before, we developed an algebra of linear transformations, which seems weird, but we noticed that you can actually define a sensible notion of a multiplication and a very reasonable notion of addition and scalar multiplication, and you kind of do algebra with linear transformations. Surprising. The nice punchline of which was that, for the certain kinds of linear transformations that we're interested in from section 4.2, constant coefficient linear differential operators, so the section 4.2 kinds of differential equations, they just really look a lot like regular old algebra. In particular, polynomials factor just like they did back in high school. Okay, and this has some really nice consequences. So where we ended last time, we went through this a little quickly, so let me go ahead and do this again. Taking our constant coefficient linear differential operator, rewriting it as a factored polynomial, allows us to do the following. We look at this equation, and let's take all of this business and shuffle the terms around. Right? It's perfectly legal to do that. Everything in sight commutes. And as a result, here, I guess I'll zoom back in. As a result, I can isolate one of these factors. And now, to the question of how can I find a solution to this differential equation, we actually have a pretty straightforward, kind of smart alecky, but nevertheless, pretty reasonable answer. If I can make that zero, we're good, right? We win. If this thing in blue is zero, clearly the equation works. And I can make that thing in blue zero by just interpreting that as a differential equation of its own. It's a very different differential equation. It's first order. It's familiar first order. It's a natural growth equation, and we know the solutions. So what's nice about this is, I mentioned this last time, 10 days ago, but when we first wrote down solutions to 4.2 differential equations, we just kind of pulled the solutions out of thin air. We just said, hey, I got an idea. Let's try exponentials with no motivation at all given. Right? I just said, hey, let's just try what's going to work. Right? So what I like about this argument here is that it gives a motivation for why that was a reasonable thing to try. I don't have to rely on having, the divine insight. My inner oracle told me to try exponentials. Here's a motivation for trying exponentials. This equation relates to that equation, which is solvable. So I think that's really nice. Okay. Here's a couple more things that we can do with this brand new algebra that we have. Again, the purpose of this algebra that we've developed is to be able to prove theorems that previously we did not have the tools to be able to prove. There being two big ones we'll get to very soon. But first, a quick observation. Let's look at this thing, d minus r. D minus r does something very convenient and simple to functions of that sort. X to the k, e to the rx. Let me just show you the punchline before we get to the demonstration. But what d minus r does is it turns one of those kinds of functions into a function of kind of the same form. It's still a power of x times an exponential, pretty much, with two slight modifications. Obviously, there's this constant out front. This constant out front's not going to be all that interesting because most of the time we're talking about making stuff equal to 0, at which point a scalar constant kind of doesn't matter, right? But anyway, it's there. And the main thing that happens, though, d minus r takes a function of this form and reduces the power of x by 1. That's the main thing you want to think of. You know, what does d minus r do to these functions? It kills off one factor of x. It's a good way to think about that. Okay. All right. That is when there are factors of x to kill off. When there are none, what does d minus r do to just an exponential? Well, you calculate it out and you just get 0. Let's do these calculations now that we've seen what the result is. What does d do to that function? Well, d means derivative. Product rule. Right? Just take the derivative of the product rule. Nothing hard there. What does minus r do to this thing? Well, minus r, it multiplies by minus r. And you can see right here that that cancels with that, and as claimed, we're left with just that one term. Easy little calculation. Likewise, an easy calculation to show that this is true. You take e to the rx, look at its derivative, right? Subtract r times itself, and you get 0. Okay. All right. Okay, so we're going to use these results, these two results here, of what d minus r does to these kinds of functions, and we're going to prove some big theorems. So here we go. Let's start off with from section 4.2. Do you remember all that business about what do you do when the characteristic polynomial has a root with a multiplicity? All right, there's the root and there's the multiplicity. And we made this assertion back then. That's a long time ago, but we asserted that if your characteristic polynomial has a root with a multiplicity, what you do, you've got a root. Root means exponentials or solutions. But because of the multiplicity, you multiply by different powers of x. Y'all remember that whole thing? I just kind of asserted that worked. This is early in 4.2. This is before we even got to anything complex, any complex roots or anything like that. Yeah, just multiply by a bunch of powers of x. Never proved it. I asserted that it was true, and then I said, look, we're going to need some more powerful machinery to be able to prove this result. So for the moment, just trust me. Well, here we are. We have the more powerful machinery now. It's this algebra of linear transformations, and let me show you how we can now prove that this does, in fact, work. So here's what we want to do. We want to see what does L do to these functions y. Right? My assertion is that these functions here are solutions to the homogeneous equation. So I'm going to compute L of y, and I just want to confirm that I get 0. Okay. All right. Well, don't forget, L is a polynomial of algebra of linear transformations at this point, and by assumption it factors. It's got a certain number of factors of d minus r there. So there's our L. The y that we're testing is this right here, x to the k, e to the rx. Okay. And now all I'm going to do is I'm going to spread out this L. Specifically, I'm going to take the m factors of d minus r, and I'm going to kind of spread them out like this. I'm going to peel off k of them and put on the right, and then one more. And I'm going to put here, and then all the rest, if there are any left over, I'll put over here. How do I know I have enough? Well, by assumption, k is less than or equal to n minus 1, and that says that this can always be done. Okay. Okay, why would I do this? Well, let me remind you. We see up here that d minus r takes powers of x and kills off one of them. That's what d minus r does to these kinds of functions. So d minus r, check this out. I have here k factors of d minus r. I have k powers of x. And they just, one at a time, pair off and cancel each other. And all together, that's fine. All together, that simplifies as just that. Roughly speaking, these k factors of d minus r kind of sort of roughly cancel with these k factors of x. Yeah, there is all the, you get an extra constant factor of k out here, and you get that for each of one of several different applications. So there ends up being a k factorial. This ends up not mattering, but nevertheless it is there. Okay. Everybody on board so far? Next step. What do we do with this thing? What does d minus r do to the exponential? Obviously, this k factorial is just a constant. I can pull it out front. It doesn't really matter. So I have d minus r times an exponential, and that is 0. And so we win. Right, L of y is equal to 0. Therefore, these yellow functions that we asserted back in chapter 4, way back when we asserted that those were homogeneous solutions, we see now by direct calculation that they are. How are we doing? Everybody on board? Okay, this calculation, I mean, there's a point of view that says, well, this is just a kind of a fancy, a shorthand for calculations that we could have done by brute force with derivatives. And to that I say, not really, because we had to be able to factor the algebra here. The fact of being able to rewrite P of D as a succession of factors. That's kind of calculus that we've never written down before. Arguably, what we have here is kind of a sophisticated, a super sophisticated kind of a product rule or something that doesn't exist in Calc 1 classes. So we really need specifically this algebra to make this proof work. Okay. All right. So we have finally proved that result from a long time ago. All right, last one. Y'all remember a theorem that looks kind of like this. Looking at particular solutions, suppose that your right-hand side takes a certain form. By the way, I know that's not the form that we wrote down back in chapter 4. Bear with me a moment. If the right-hand side takes a particular form, we saw that there were sort of two different cases. On the one hand, if r is not a root, then we have a naive guess that works. And on the other hand, if r is a root, then here is a modified guess. We have the unfortunate coincidence. Then we multiply our naive guess times this magic fix-it factor of x to the m, right? Where don't forget the multiplicity is what tells you how many factors of x to multiply by. Okay, now we're not going to prove this theorem completely here today. I'm going to assert, though, that part of it is pretty plausible. Let's look specifically at this business here, right? Part 1. We've seen several examples where this works out. This is you can see how this ought to work out. I mean, when you take a function of this form and plug it into the equation, you can see you've got all the kind of different terms that seem like they ought to be able to pair each other off and balance each other out, and ought to work. We could prove this. It would just take some time, and I think this assertion here is sufficiently plausible that I don't think it's a good use of time for us to actually prove part 1 here. I'm just going to say part 1 is pretty believable and pretty well motivated, which I think will be fine for Math 216. However, not so with part 2. This business about, hey, just multiply by x to the m and everything magically works out. I have not given you a very good reason to believe this is true. Right? This is still kind of a hocus pocus kind of thing, right? So that's what I want to talk about. I'd like to persuade you. Why is it that the x to the m makes sense? Now, before we go on, let me come back to this isn't the same theorem. And that's true. This that I've drawn there, a x to the k, e to the rx, it looks like it's missing all the sine and cosine stuff, right? What we wrote down back in chapter 4 was monomial times exponential times sines and cosines. They're actually kind of in here, sort of. Specifically, this r is a complex number. And remember that when you have e to the power of a complex number, you multiply that whole thing out and, apply Euler's formula, etc. You get exponentials times sines and cosines. Okay, now, still not exactly the same form that we saw back in chapter 4, but I'm going to say it's pretty close, and in fact, linear combinations arguments can fill this in. So in particular, every one of these functions that we're addressing in this new theorem, every one of these is a linear combination of functions of the sort that we've already considered in 4.3. Section 4.3. And furthermore, remember this algebra goes the other way. I can view these functions, exponentials times cosine, exponentials times sine. By playing clever linear combinations arguments, I can view each one of these as linear combinations of functions that look like this. So what I'm going to say is that even though, yes, this is a different theorem, this is a very similar theorem. These are what you might call equivalent theorems, in that you can use this one to prove that one, and you can use that one to prove this one by just making linear combinations arguments, and it works out just fine. So they're kind of sort of the same theorem. Now, why am I showing you a different one here? Reasonable question. Well, in chapter 4, we chose the real version, the non-complex that is. We chose the real version because I wanted to show you all how to actually use that to solve real differential equations for real world applications that y'all are going to see in your engineering classes, right? And in that real context, the real version makes sense. And so that's why I put in the sines and cosines in that context. Here in chapter 5, we're just trying to get a motivation for what's the deal with this x to the m, right? So what we're doing here is not going to go immediately to applications. I'm just trying to do some algebraic motivations here. For algebraic purposes, this version, the complex version of the equation of the theorem, is actually easier to work with because it doesn't have any sines and cosines in it. Right? Again, they're morally equivalent theorems, and they have their advantages and disadvantages in context. In this context, this one's more convenient. All right. Okay. So, what's the deal with that x to the m? Where does that come from? Reminder. We're trying to understand this L. Don't forget we've rewritten L with algebra of linear transformations. Don't forget by assumption we're looking at the characteristic polynomial as having R as a root of multiplicity m, which means that. Right, our characteristic polynomial has a root, so a factor of d minus r. Multiplicity m means that factor of d minus r appears m times. Okay. So, the function that we're looking at, that function, let's write that down, here it is. We put in this extra factor of x to the m that we're trying to understand here, what's the motivation for putting in this factor of x to the m. And having written it together like this, you can kind of see this same sort of thing happening. We've got this constant coefficient operator, factored. We've got this function with powers of x. We've got some d minus r's, therefore right next to powers of x. Don't forget what d minus r does to these kinds of functions. D minus r kills off factors of x. I have I have m factors of d minus r on the left. Each one of these m corresponding factors of x will cancel one of them out. Okay, now, going back, don't forget, yes, have to concede that killing off a packed factor of x is not the only thing that happens. There's also a scalar that appears out front, and so as a result of that, what that means is these coefficients here are not going to be the same as those coefficients. The C numbers will be different from the D numbers, but predictably different. And we can just keep track. We know exactly what the powers of x are. We know exactly how many times we're applying this operator. Then you can just write down basically a factorial formula that tells you the relationship between the C numbers and the D numbers. If you know some of them, then you know the others. And the advance. So what's happened? Why is this a win? Well, notice that what has resulted is a differential equation that we already know how to solve. What we have here is one of these cases. We have here a linear differential operator, constant coefficient. We have an alleged hopeful particular solution that we want to make everything work out to be g of x. This polynomial q does not have r as a factor at all. We know it doesn't because all the factors of r have been pulled out already. So r is not a factor. R is not a root. And since r is not a root, the naive guess works. And so you can solve for all these d's. And having solved for the d's, again, there's a predictable relation between the d's and the c's, so you can solve for the c's, and therefore you have a solution to the original equation. So there's a lot of little details in there. Try not to get lost in those details. The point to this, let me erase everything that isn't the point. The point is that we put these factors of x in there to balance off with these factors of d minus r that are messing things up for us to reduce the question to the previous, case one where there's no roots and everything. The naive guess works just fine. Roughly speaking, the x to the m comes from the factors of d minus r to the m that were there by assumption. Okay, so a lot of algebra, a lot of details. You don't need to worry about following through all the details. I just wanted y'all to see this plausibility argument, and therefore, because of this, why is it that multiplicity m has you put in these extra factors of x to the m? Well, kind of plausible. That's what I want y'all to take away from this. How are we doing? Is everybody happy? Any questions? Okay. Okay, so moving along. We're going to go to section 5.3 now. We'll start off with a little bit of a flashback. Back in 5.1, we talked about these kinds of functions. Well, we've talked about these kinds of functions a million times. You can interpret a matrix as a function. This has nice applications in interpreting determinant, for example. So what we saw back in section 5.1 is that if you have such a function, it is a linear transformation from Rn to Rm, and that's pretty easy to check, right? That was an exercise that I suggested for you guys. The way you confirm that this function is a linear transformation is put a linear combination in, do what the function says, and confirm you get the corresponding linear combination out. Okay. So, hope everybody took a crack at that. That shows only that the arrow goes this way. That shows that if you have a matrix, then you can interpret it as a linear transformation. It turns out that the statement actually works the other direction as well. So if you have a linear transformation from Rn to Rm, it also is true that you can view that function as a matrix. And this is a little bit harder to prove. It's not terribly hard to prove, but it's a little bit more, the first theorem that y'all proved back in 5.1 is just a matter, again, you just plug in the linear combinations thing and just make sure it satisfies the linearity property. Here, I'm assuming that something has an abstract property of being a linear transformation. I have no formula for how to compute it. And I'm asserting that a certain matrix exists. Right, so it's a little harder to see exactly how to get your hands on proving this. The way to get this done, the way to prove this result, is to have just the right insight of what formula to pick. I'm going to show that this matrix exists by writing down a formula for it. Here it is. A is made up of certain columns. Those columns are computed by this certain formula. That's what A is. What I'm supposed to show is that this matrix A exists and has this property. I'm supposed to show that T of X is AX, and I'm going to show that T of X is AX by direct calculation. And you can see here it is. I'm going to start with AX, and I'm going to get T of X as required here. The details of showing that are just a matter of kind of writing it down. Let's get that done. So let's see here. I'm starting with AX. Let's multiply A times X. Flash back to chapter 1, the way you multiply a matrix times a vector, linear combination of column vectors. Notice these right here that we're taking linear combinations of, my column vectors. Alrighty. Next observation. Those column vectors are the images of the standard basis vectors by construction. Right? We're choosing to write our matrix A as columns being the images of the standard basis vectors. Okay. Having done that, here's just a use of linearity. Right, here I have a linear combination of outputs, and I'm rewriting it as coming from a linear combination of inputs. Plain old linearity. By assumption, we're assuming that T is a linear transformation, so we can do that. And now it's just spike the football time, but look what we have on the inside here. That thing, this is the vector that's a linear combination of the standard basis vectors where x1 through xn are the coefficients in the linear combination. That is the x vector, as we observed again way long ago. In fact, that's a Math 212 observation. So, as required, done. So this is a tricky proof. The arguments here are not terribly tricky. I do use some nice feature. I use a sort of Math 216 point of view on matrix multiplication here. We use linearity, and we use our choice. We use our construction here. Right. The hard part about this proof is at the very beginning, where we have this seemingly magical insight to let's just choose this. Let's just define the matrix A to be defined by, its columns are the images of the standard basis vectors. That's the tricky part. And you shouldn't think to yourself, how would I have thought of that? That's just the tricky thing that makes it work. Okay. But it remains. That's the thing that makes it work. And so this is an important one to remember. If you have a linear transformation and you want to, from Rn to Rm, if you want to represent that linear transformation as a matrix, the columns are the images of the standard basis vectors. That's the formula. Yes?
What does that mean, images of the standard basis?
Yeah, images just means what comes out, right? So the fact that we're looking at T of something means that we're looking at this thing here is the image, namely the output from that vector there, and that vector is one of the standard basis vectors. You remember the standard basis vectors are like ones and zeros? Yeah, right. Okay. Anybody else? Good question. Thank you. Very good. Okay. All right. So I want to show you an application of this theorem. I'm going to show you a linear transformation that you've seen before, that you probably didn't think of as being a linear transformation. It's going to seem weird, in fact, that it's but anyway, it is. So I'm going to give you a linear transformation, and from that, we're going to show how to compute it by way of not only a formula, but by way of a really convenient formula involving just matrix multiplication. So the linear transformation in question is a rotation. Rotation in R2, around the origin. Now, I didn't draw the picture of this in the notes, so let me draw it down here, but I want to try to persuade you that rotations around the origin are, in fact, linear transformations. So here's my picture. Suppose I have R2 here. Suppose I have a couple of vectors. So one of our requirements, arguably two requirements to have a linear transformation. One is it's got to commute with addition. The other is it's got to commute with scalar multiplication. You can also talk about commuting with linear combinations. I find it more convenient here to break it into two separate steps. So let me argue that rotation commutes with addition. So I'm going to try to show that if I add first and then rotate, that's going to be effectively the same as if I rotated and then added. The way I'm going to prove that is by drawing a couple of parallelograms. So there's a parallelogram. Now let me rotate this entire parallelogram. Okay, not bad. Got a parallelogram that I then rotated to make another parallelogram. Really, this is kind of the proof right here, but let's talk through, what would it mean to add and then rotate? What would it mean to rotate and then add? And everything that is involved in that process is visible on the picture right here. So, two original vectors. If I add and then rotate, that gives me that point. On the other hand, if I were to rotate first and then add, it gets me to the same point. You're just doing the addition on the rotated parallelogram instead of adding on the original parallelogram and rotating. But the geometry is the same in arguably both cases. Does everybody see how this is pretty plausible if you think about it? Rotate the picture. So anyway, something to play with, but I claim that this works just fine, and so rotations are linear transformations. This theorem then says, because it's a linear transformation, I can compute that rotation with matrix multiplication, and furthermore, here's a formula for how to find my matrix. Just look at the standard basis vectors, rotate them, and make those the columns of your matrix. Okay, so let's do that. Now this is just a little bit of trig. I know y'all remember all your trig from way back when. So here's E1. Here's the rotation of E1 by some angle theta. And simple trig tells you that the coordinates there are cosine theta, sine theta, right? Easy trig, flashbacks, high school. On the other hand, here's E2. Here's the rotation of E2. Again, easy trig. This angle here being the same theta, that's theta. I emphasize theta is not that angle. right? That's theta plus pi over 2. So theta is that little angle. And anyway, think through the trigonometry of this little triangle, and you come up with this formula. And just like it says on the previous page, the image of the first standard basis vector is your first column. The image of your second standard basis vector is your second column. And there's your rotation matrix. If you want to rotate any vector in R2, any vector at all, whatever, and you want to rotate by any arbitrary angle, let's just make it a silly example. If you want to take the vector 17, 4, and you want to rotate by 22 1/3 degrees, there's a matrix. Matrix times vector, done. Want to see how that works? So this is really a pretty shocking result that you can do this. It seems like, if you're doing a rotation in R2, it seems like that should ultimately shouldn't that be a geometry problem, like a really hard geometry problem? And there's triangles involved, but they're not right triangles, and they're tilted, and everything it seems like it ought to be weird and stuff. We turn this into a couple of quick steps. The big thing that makes this work is the biggest step in the argument is this one right here, to observe that we're talking about a linear transformation. There are very few linear transformations in some sense. Knowing that you have a linear transformation is extremely powerful. It gives you this amazing ability to compute any value of the function simply by knowing two values of the function and to capitalize on linearity. Okay, yes?
How would you write
Yeah, that's a great question, and we are going to talk about that. We won't get to that today. That'll be a Friday thing. But yeah, that's the next thing we're going to do. We have to kind of build up to that, though. Yeah, it's a great question. Anybody else? Okay. Was that a hand? Yeah, okay. Yeah.
Can you just say one more time what proving this helps us with?
Yeah, so this allows you to rotate any vector that you'd like. So let me clear out the mess here. If you want to rotate by any angle theta, any vector x, right? Now, it wasn't hard to rotate E1, and it wasn't hard to rotate E2 because you get nice little right triangles that are lined up very nicely on axes, and it's familiar trick. But if you take the vector 17, 4, right, let's take something like, something like that, some random wacky vector, and you want to rotate that by some random wacky angle, theta, right, where theta might not be a convenient angle, and this original vector might not be a convenient vector. As a high school geometry problem, that's really, really hard because you can draw yourself a little triangle, but the triangle is tilted, so it's like you're tilting a tilted triangle. And it's not clear how you do that. But it ends up being really simple if you just capitalize on the linearity and use interpret the linear transformation as a matrix. That's the point. Yeah. Yes.
So the cosines and sines of the matrix A will stay the same. It's just the theta that's changing.
Yeah. That's right. So in fact, this is not a bad little formula to memorize, right? This is the rotation matrix in R2, and it's always, as you say, it's always the same exact formula, just with different thetas depending on how much you want to rotate counterclockwise. Yeah. Right. Okay. So. Now, we find ourselves in a slightly weird situation. We already knew that a matrix is a linear transformation, and now we know that a linear transformation is a matrix. So what we've seen, at least in Rn, what we've seen is that if you give me a matrix, there is a corresponding linear transformation and vice versa. So there's a perfect pairing between matrices and linear transformations. You give me one, I give you the other. They're kind of not. It's not like they're exactly the same thing, but you can kind of think of them. Certainly they behave the same ways in Rn. Right? Not that there's anything wrong with that. But here's the weird thing. With matrices, we had a product. We had a multiplication. Sure. with linear transformations, we had a multiplication. Now, when these were separate objects that we didn't sort of, identify with each other, well, there's a multiplication of these things and it's over here. And there's a multiplication of these things and it's over here. But now we're saying, hey, these are kind of the same thing. So now what I kind of have, approximately, is two different multiplications on sort of the same thing. So, for example, here's the problem I have to worry about. If I were to take two linear transformations and multiply them as linear transformations, and then think of that product transformation as a matrix, is that matrix the same as what I would have gotten if I multiplied the two individual matrices as matrices? It is not obvious that this is true. I mean, in fact, here, let me elaborate on how not obvious this is. What was the connection between how we decided to write down matrix multiplication and how we decided to write down linear transformation multiplication? We didn't make any connection at all. With matrices, we just wrote down a weird formula. And I said, here's the formula. And y'all said, okay, weird, but whatever. And then for linear transformations, we made no reference at all to that. Completely said, hey, here's a completely different point of view. I want to think about compositions as defining this product. We define them in totally disconnected, unrelated ways. Why would we have the audacity to think that they're the same when they overlap? So this is a serious worry, because it'd be nice to be able to take advantage of the fact that, hey, transformations are matrices and matrices are transformations, and it'd be kind of nice to just kind of toss around the algebra without having to worry. And wouldn't it be weird if we had two products that didn't equal each other? That's a big, nasty worry. And the good news is it all works out. It's a big sigh of relief, but it does. If you compose two linear transformations, thus making a product transformation, if you look at the matrix representing it and ask, how would you compute this matrix? There's a little bit of algebra to do, but that matrix is the product as matrices. So said differently then, multiplication of linear transformations corresponds perfectly with multiplication of matrices. And again, big sigh of relief. We got lucky there, in fact, one could argue, given the way we set these things up. Here's a different point of view on that, though. Back in section 1.2, when I never gave you any motivation for how we define matrix multiplication, the reason we did it the way we did it was so that this would work out. One way of saying it. I said differently, we define, you can motivate the formula that back in 1.2 for how to multiply matrices by thinking, okay, thinking of these matrices as representing linear transformations, how would you compose these as linear transformations, and then what's the matrix representing them? That's the best way that I'm aware of to motivate the formula for matrix multiplication. Okay, and of course they do not tell you this in high school when they're showing you matrix multiplication. They couldn't realistically do it, but that's my point of view on it anyway. Okay, let me show you where I think this is really, really valuable. Associativity of matrix multiplication. You'll notice we never proved that way back when. This is something that we've been using, but we never proved, right? So, why didn't I prove it? Well, the book wrote down the proof in section 1.2, and it's perfectly rigorous, and it's perfectly fine, and it's also extremely opaque and unsatisfying. And I encourage you to pick up a copy of the book, flip back through it, and look and find that proof where the book proves the associativity of matrix multiplication. And what you're going to find is there's a bunch of sigmas and i's and j's and algebra that's perfectly rigorous, and it gets down to the answer, and there's no intuition to be had. Right? So very unsatisfying. I didn't do it because I wanted to wait and show you this much more satisfying proof that comes from taking advantage of the fact that multiplication of matrices corresponds, as we know now, perfectly with multiplication of linear transformations. And don't forget, multiplication of linear transformations, we have a really easy motivation. What does it mean to multiply two linear transformations? It means compose the functions. Right? So, how do I know this is true? This is an easy thing to prove. This is just a matter of writing down, what does this, as a function, what does that do to some vector x? Versus what does this do to that same vector x? Just like we did way back when, when we were proving properties in algebraic linear transformations. In fact, this was on the list. And compute both sides here and just observe that up on top, what we have is we're going to take x, we're going to first do t, after which we're going to do s, dramatic pause, and then we're going to do r. Whereas down here, we're going to take x, we're going to do t, dramatic pause, and then do s, and then do r. In all cases, we're going to take x, we're going to do t, and then we're going to do s, and then we're going to do r. The only difference between these two calculations is where's the dramatic pause. And no surprise, you get the same result in both cases. Both of these are R of S of T of X. So let me address the question now, again, that we kind of skipped over in 1.2. Why is matrix multiplication associative? Is it because of sigmas and subscripts, I, J, K, and all, moving those symbols around? Don't think of it that way. Matrix multiplication corresponds with composition of linear transformations, and compositions are obviously associative. I mean, it's just immediately clear that when you compose functions together, it doesn't matter where you put the parentheses. So I find that much more satisfying. I find that that's why this not only is true, that's why this should be true. That's like I say, I'd rather give you this proof than make you wade through all that stuff in 1.2. Okay, I've got a couple minutes left. I want to set up a little bit of context for the next thing that we're going to do. I want to remind you of an old fact about bases from way back when. If you have a basis for a vector space, this goes back to section 2.4.